Hi, I'm Hayato Shimabukuro from Yunnan University, CIFR. Today, I will give a talk about recovering H bubble size distribution from 21 cm power spectrum with neural network. So here, I briefly start the history of the universe. Here, I show the history of the universe. Left panel shows past universe, and right panel shows present universe. When we look up the sky at night, we can find many stars. However, the early universe is dark because there was no bright objects such as stars and galaxies. We call this epoch Dark Ages. After first generation stars and galaxies had formed, they illuminated the universe. We call this epoch Cosmic Dawn. Until first stars and galaxies had formed, the universe have kept neutral state. As the universe evolves, ultraviolet photons emitted by luminous objects ionize the intergalactic medium IgM. We call this epoch of reionization or EOR, and our study focuses on the EOR. As a promising tool to probe the EOR, we focus on the 21 cm signal. Neutral hydrogen atom has different energy level between singlet and triplet states, so they emit radiation according to its energy difference. The 21 cm signal is emitted by neutral hydrogen atom due to hyperfine structure. The observable of the 21 cm signal is brightness temperature, represented by this form. The important thing of the 21 cm signal is that it includes both cosmological and astrophysical information. Observationally, we first try to detect 21 cm signal statistically. As such quantity, we focus on 21 cm power spectrum. The 21 cm power spectrum is two-point correlation function in Fourier space shown by this formula. Here, we show the 21 cm power spectrum as function of wavelength and as function of redshift. The left panel shows the 21 cm power spectrum as function of scale dependence, and the right one shows the 21 cm power spectrum as function of redshift. We can extract information from the 21 cm power spectrum. For example, typical ionized bubble size. As you can see, we can find characteristic peaks in the 21 cm power spectrum as function of redshift. So, one of the questions during EOR is how large bubbles are distributed in the IgM. To evaluate this question quantitatively, we often compute ionized bubble size distribution. If we know ionized bubble size distribution, for example, we can learn properties of ionizing sources and some astrophysical effects such as ionizing efficiency, recombination, and radiating feedback. Furthermore, we can also study how dark matter halo is related to ionized bubble, that is to say, bias problem in cosmology. Here, I introduce traditional method to measure bubble size distribution. First of all, I want to emphasize that we do not observe 21 cm image directly by radio interferometer. Instead of observing 21 cm images, radio interferometer provides us visibility, which is Fourier transformation of image map. Therefore, we need to perform inverse Fourier transformation to obtain 21 cm image. Finally, we compute bubble size distribution from 21 cm images. However, we cannot avoid incomplete inverse Fourier transformation because the number of antennas in radio interferometer is limited. On the other hand, we can directly compute 21 cm power spectrum from visibility without inverse Fourier transformation. This means that we can avoid information loss by incomplete Fourier transformation. So, our strategy is that can we recover bubble size distribution from the 21 cm power spectrum with neural network? So here, I briefly introduce the artificial neural network called ANN. Here is the image of brain, human brain. Human's brain consists of neurons and they connect each other. The function of our brain, such as memory and recognition, works by connecting neurons. An ANN is a mathematical model of human brain network. Historically, the basic idea of the ANN is suggested in 1980s. Recently, they have been focused such as deep learning because of development of computer resources and we can obtain huge amount of data. So, and currently, the ANN also has been applied to the field of astronomy. Here, I introduce the ANN. The ANN consists of three kinds of layers: input layer, hidden layer, and output layer. Each layer has neurons and they connect neurons at the next layer. We can increase the number of hidden layers and we call the ANN with multiple layer deep neural network. The purpose of the ANN is to construct approximate function between input data and output data. For this purpose, we prepare training data and train architecture of neural network with training data sets. Once we train neural network, then we can apply trained neural network to unknown data for prediction. In our ANN, we construct neural network between 21 cm power spectrum and ionized bubble size distribution. That is to say, we establish approximate function between the 21 cm power spectrum and ionized bubble size distribution. Then we can recover ionized bubble size distribution from 21 cm power spectrum when we use 21 cm power spectrum as input values. Here, I show the result. The top panel shows the bubble size distribution of ionized bubble obtained by neural network and obtained from 21 cm 3D image directly. And the bottom panel is absolute error between the bubble size distribution obtained by neural network and bubble size distribution obtained by 3D image directory. And the red dashed line shows bubble size distribution recovered by the 21 cm power spectrum with neural network, and black solid line represents the bubble size distribution obtained by 21 cm 3D image directory. And in this case, we focus on the neutral fraction. Neutral fraction is 0.39, and in that case, R2 squared score is 0.957, and R squared score is that which represents the accuracy of the regression problem. And if R2 score is close to 1, then regression works well. And if R2 score is close to 0, then the regression does not work well. And in this case, R2 score is 0.957. So this means that the recovery of the bubble size distribution by the ANN works well. So far, we see the bubble size distribution at the fixed neutral fraction Here, I show the bubble size distribution at each stage of reionization. And here, I show the bubble size distribution at neutral fraction is 0.3, 0.51, 0.67, and 0.8. And as you can see, the ANN can recover bubble size distribution at each stages of reionization. Next, we include thermal noise in input 21 cm power spectrum. We compute 10 realizations of thermal noise and try to recover size distribution. And as observational noise, we assure future observation SKA. And here, black solid line shows the bubble size distribution obtained by 21 cm 3D image directly. And gray shade region is recovered bubble size distribution by the ANN with noise 21 cm power spectrum. And bottom panel shows the absolute error between true bubble size distribution and obtained bubble size distribution. And we can find that the recovery works well even if we consider the observational noise in the 21 cm power spectrum. We assume SKA level noise. So this is the summary of my talk. The take-home message of my talk is that EOR and cosmic dawn are final frontiers of the history of the universe, and 21 cm signal is a promising tool to study EOR and cosmic dawn. And the ANN is a new tool to analyze 21 cm signal and also other field of astronomy. And in this study, we focus on the application of the ANN to recover ionized bubble size distribution from the 21 cm power spectrum. And successfully, we can recover the ionized bubble size distribution from 21 cm power spectrum with neural network. Thank you.